A signal just reached Earth. It traveled for over 13 billion years. Scientists traced it back to a star that died before our sun was even a thought. Then they found something stranger. A star still alive today that appears older than the universe itself, and hidden in ancient radiation, possible echoes of a universe that existed before ours. We are going to visit each of these mysteries: a ghost star racing through our galaxy, a 10-second flash that outshone whole galaxies, and a theory that time itself had a before. If you enjoy the journey, subscribe and leave a like. It genuinely helps. Now brace yourself. We begin. The alert came in March of this year, and the scientists who saw it went quiet. A detector picked up a burst of energy so powerful, it briefly outshone everything around it. The signal had a return address. It came from a point in the sky so far away that the light left its source when the universe was only 5% of its current age. The team ran the numbers. Then they ran them again. The signal had traveled for over 13 billion years before reaching Earth. 13 billion years. Picture a road trip from New York to Los Angeles. Now picture driving that same route back and forth every single day for 4 billion years. That still does not get you close to the distance this signal crossed. The event was logged as GRB 250314A, a gamma ray burst, a dying star's final scream, compressed into 10 seconds of raw energy. 10 seconds. The burst that reached our detectors was short enough to count out loud. 1, 2, 3, all the way to 10, done. Over. But the energy packed into those 10 seconds was enough to temporarily outshine entire galaxies sitting nearby. What makes this strange is the timing. The star that produced this signal exploded when the universe was roughly 730 million years old. For context, the universe is 13,800,000,000 years old right now. That star lived and died in what amounts to the universe's infancy. It was one of the first generation of massive stars ever born, a pioneer of cosmic fire, and it sent us a message that just arrived. Here is where the story gets uncomfortable. When scientists started looking deeper into the data around this signal, they found other readings that did not fit. Patterns in ancient radiation that seemed to carry information from an era that should be impossible to see. The signal from GRB 250314A was just the door. Behind it sat questions that cut much deeper. How early can we actually see? What is the oldest thing in the observable universe? And is there any chance that something from before the Big Bang itself left a mark we can still detect today? The answer to that last question depends entirely on which physicist you ask. Some will tell you the idea is ridiculous. Others will tell you the evidence is already sitting in our data, waiting to be confirmed. Both sides have reasons to believe what they believe. Both sides have reasons to worry they might be wrong. What everyone agrees on is this: we are living in a moment when our tools have finally become powerful enough to look back almost to the very start. The James Webb Space Telescope is peering into the universe's childhood. Ground-based detectors high in the Andes Mountains are pulling signals out of the ancient sky that would have been invisible a decade ago. And every new discovery is either confirming what we thought we knew or quietly dismantling it. The burst from GRB 250314A did something specific when it arrived. It forced astronomers to ask how well they actually understood the early universe. The answer came back with uncomfortable gaps. Those gaps are where we are headed. Each chapter from here moves further back in time, closer to the start, closer to the moment everything we know either began or continued from something we have never seen. And somewhere in that earliest darkness, there may be a signal still waiting to be heard. Every detective story needs a starting point. For the universe, that starting point is 13,800,000,000 years ago. Scientists call it the Big Bang, a moment when all of space, all of time, all of matter, and all of energy erupted from a state so small and so hot that our best math cannot fully describe it. Everything that exists came from that single event. Every galaxy, every star, every atom inside your body right now. Here is what that means for our story. If the Big Bang was the beginning of time itself, then nothing can be older than it. There was no before to come from, there was no space to travel through. There was no clock ticking somewhere else waiting for the universe to arrive. Time started at the Big Bang the way a movie starts when you press play. Before that button press, the movie does not exist in any form. This seems simple. It is actually one of the most mind-bending ideas in all of science. When we say the universe is 13,800,000,000 years old, we mean time itself is that old. Space itself is that old. So when a signal arrives that appears to predate that moment, physicists do not just raise an eyebrow. They question whether the signal was measured correctly, whether the model is right, or whether something is happening that no textbook has accounted for yet. The standard model of cosmology, which is the framework scientists use to explain how the universe formed and expanded, treats the Big Bang as an absolute wall, a hard stop. Light cannot come from before it, because light did not exist before it. Particles cannot travel from before it, because particles did not exist before it. But here is the crack in that wall. Some theories suggest that what we call the Big Bang was actually a transition, not a true beginning. A moment when one state of existence collapsed and another exploded into being. If that is true, then the wall has a door, and signals from the other side might have slipped through. This is still theory. Confirmed science says the Big Bang is the boundary, but confirmed science also keeps finding things near that boundary that do not fully make sense. GRB 250314A was born at 730 million years after the Big Bang. That is early, but it fits inside the boundary. However, the radiation surrounding the early universe, the ancient glow that fills all of space, contains patterns that some scientists believe carry information from before that boundary. We will get to those patterns. They are some of the strangest data in all of astronomy. For now, understand the stakes. Every time we push our instruments toward that 13,800,000,000 year wall, we are testing the most fundamental idea in cosmology. Either the Big Bang was a true beginning, in which case nothing older can exist, or it was a chapter break in a much longer story, and the previous chapters left fingerprints. Those fingerprints would not just rewrite textbooks. They would force us to rethink what time actually is, and what it means for something to truly begin. The next piece of this puzzle is not a signal from a dead star. It is a living star, one that by every measurement we have should be impossible. 190 light years from Earth, roughly 1,117,000,000,000 miles away, there is a star still burning in our galaxy right now. It looks ordinary from a distance, a dim point of light drifting through the Milky Way like millions of others. But when astronomers started measuring how old it was, the number they got back stopped conversations in research labs around the world. The star is called HD 140283. Astronomers nicknamed it the Methuselah star after the oldest person in the Bible said to have lived for 969 years. The nickname stuck because the star's measured age came back at 14,460,000,000 years old. The universe is 13,800,000,000 years old. That means this star appeared to be older than everything, older than the galaxies around it, older than the space it travels through, older than time itself according to our best measurements. A living contradiction sitting less than 200 light years from our solar system. Close enough that if you had a fast enough ship, you could theoretically visit it within a human lifetime measured by the ship's own clock. Scientists were not ready to throw out the laws of physics over a single star, so they started pulling the measurement apart, looking for where the number could have gone wrong. Age measurements for stars work through a specific process. Astronomers study the light a star gives off, analyze its brightness, its color, and the chemical elements it contains, then compare those readings to models of how stars live and age. The older a star is, the more it has burned through its original fuel, and that burn rate is reflected in the light. The Methuselah star's light came back with a signature that matched the absolute oldest stellar models astronomers had. A star born in the universe's earliest era, when conditions for making stars were almost nothing like they are today. Here is what made it genuinely alarming. The age estimate was not just slightly over the universe's age, it was over by more than 600 million years. That is a gap wide enough to be a serious problem, not a rounding error. The scientific community did not panic, but it paid very close attention. Because if the star really was older than the universe, one of two things had to be true. Either our measurement of the star's age was wrong, or our measurement of the universe's age was wrong. Both numbers come from some of the most precise tools humanity has ever built. Both had been checked thousands of times by different teams using different methods. And yet, here was this quiet, ordinary-looking star drifting through our galaxy, carrying an age that broke the math. The deeper researchers dug, the stranger the situation became. The Methuselah star was ancient in ways beyond just its years. Its chemistry told a story of a universe that barely existed yet, a cosmos so young it had barely produced the ingredients needed to build stars at all. Something very strange was going on with this star's past, and figuring out what required looking at the universe's very first chemistry experiment. Measuring how old a star is sounds like guesswork from a distance. It is actually one of the most precise things astronomers do, and the Methuselah star forced that precision to its absolute limit. The method starts with light. Every star produces a unique spectrum, which is a fingerprint of the elements burning inside it. When you split starlight through a special instrument, it breaks into bands of color. Dark lines appear at specific points in that color spread, and each dark line corresponds to a specific element. Hydrogen, helium, oxygen, iron. Each one absorbs light at a slightly different wavelength, leaving a mark as clear as a barcode. Scientists use this fingerprint to figure out what a star is made of. From that, they can figure out when it formed. Here is the key. The universe started with almost nothing. In the first few minutes after the Big Bang, only hydrogen and helium existed in large amounts. Every heavier element, carbon, iron, gold, oxygen, everything else had to be created inside stars and scattered across space when those stars exploded. The older a star is, the less of those heavy elements it contains, because it was born before most of those elements were produced. Astronomers call the measure of heavy elements in a star its metallicity. A star with high metallicity is young. A star with low metallicity is old. The Methuselah star has some of the lowest metallicity ever recorded. It contains almost no iron at all. That single fact alone screams ancient. Beyond metallicity, scientists use a star's position on what is called the Hertzsprung-Russell diagram, which maps stars by their brightness and temperature. As stars age, they change position on that map, in predictable ways. The Methuselah star sits in a region that models associate with extremely old, evolved stars that have been burning for a very long time. Both methods pointed to the same conclusion. The star was extraordinarily old. The problem was getting the precise number right. To calculate exact age, astronomers also need to know the star's exact distance from Earth. Distance affects how bright a star appears, and brightness feeds directly into the age calculation. Get the distance wrong, and the age comes out wrong too. When the Methuselah star's age first came back at 14,460,000,000 years, the distance measurement being used was slightly off. The star appeared dimmer than it actually was, which made it look older than it actually was. Astronomers went back and used updated distance measurements from a European space observatory called Hipparcos, which had been mapping stellar positions with extreme accuracy. With the corrected distance, the calculated age dropped. The new best estimate came out at 13,660,000,000 years. Still ancient beyond imagination, still one of the oldest objects ever found, but now sitting inside the possible range of the universe's age. Once the error margin was factored in, that error margin is plus or minus 800 million years, which means the star could be as young as 12,860,000,000 years, or as old as 14,460,000,000 years. The low end is safe. The high end still breaks the universe's timeline. The star is not fully resolved. The question of its exact age is still open. And that open question points towards something even older, a signal so ancient it predates every star that has ever existed. 800 million years sounds like a comfortable cushion. In everyday life, a margin of error that large would feel absurd. If a doctor told you your test results were accurate, give or take 800 million of anything, you would ask for a different doctor. But in astronomy, working at distances of trillions of miles, measuring objects that formed over 13 billion years ago, an 800 million year margin is considered impressively precise. The Methuselah star's age lands at 13,660 million years, plus or minus that 800 million. What that range actually means for scientists is both reassuring and quietly unsettling. On the reassuring side, the low end of the range puts the star at about 12,860 million years old. That fits comfortably inside the universe's confirmed age. The universe would have had time to form the star, no paradox, no broken physics. On the unsettling side, the high end of the range puts the star at 14,460 million years. That is still 660 million years older than the universe itself. 660 million years is enough time for entire civilizations of stars to form, live full lives, and explode. That is not a small difference. And here is the uncomfortable truth about that margin. It comes from the limits of our instruments. We cannot measure the star's distance with perfect accuracy. We cannot fully account for every variable in the models we use to calculate stellar ages. The 800 million year range represents how much uncertainty still lives inside our best science. Scientists did not simply accept the revised estimate and move on. They kept studying the star, refining the models, checking the distance measurements through multiple independent methods. Each new check narrowed the range slightly, but never eliminated it. What the Methuselah star exposed is a deeper problem in astronomy. Our models for how stars age are built on physics we believe to be correct. But physics can have gaps. If any of the assumptions inside those models are slightly wrong, the age estimates built on top of them carry that error forward, quietly, invisibly, until something like this star forces it into the open. One team proposed that the star might have slightly more helium in its core than standard models assume. That extra helium would affect how the star burns, which would make it appear older than it is. A small invisible difference in composition, compounded over billions of years, could shave hundreds of millions off the age estimate. That adjustment has not been fully confirmed. It remains a promising lead. What remains confirmed is the star's extreme age and its extreme rarity. In the entire Milky Way galaxy, astronomers have found only a handful of stars this old. Each one is a direct survivor from the universe's first era. Each one formed from gas that existed before the first supernovas scattered heavy elements across space. They are the closest things to living fossils that the cosmos has produced, and the Methuselah star is the oldest of them all, or at least the oldest one we have found so far. But old stars are still young compared to what comes next, because the oldest signal in the universe predates every star, every galaxy, every object that has ever formed. It is not light in the traditional sense, and for a long time we had no idea it was even there. Go back far enough, and the universe stops looking like anything you can picture. 1 second after the Big Bang, the universe was a fireball smaller than your city, packed with temperatures over 18 billion degrees Fahrenheit. Everything was plasma, pure raw energy, particles smashing into each other so fast and so hard that nothing could hold together, no atoms, no molecules, no structures of any kind. Think of it like a blender running at full speed with the lid off. Every time something tried to form, the heat ripped it apart again. Protons and neutrons slammed together and immediately separated. Electrons flew around with nowhere to settle. Light itself could barely travel more than a short distance before colliding with something else and getting absorbed. This first second matters enormously for our story because it set hard rules about what signals could survive to reach us today. In that furnace, two types of particles behaved very differently from everything else. One was the photon, which is the particle that makes up light. Photons were everywhere, but they were trapped. The plasma around them was so dense that photons bounced around inside it like ping-pong balls in a room with no exit. They carried energy but could not escape to tell us anything about that moment. The other particle was something different, something smaller, faster, and almost impossibly antisocial: the neutrino. Neutrinos are particles with almost no mass and no electric charge. They barely interact with anything around them. A neutrino can pass through a wall of solid lead 1 light-year thick and come out the other side without touching a single atom. They are the universe's most unsociable traveler. In the first second after the Big Bang, neutrinos were interacting with the surrounding plasma through the sheer force of the temperature. The energy density was high enough to keep even neutrinos engaged with the surrounding matter. But at exactly 1 second after the Big Bang, the universe had expanded and cooled just enough to hit a critical threshold. The neutrinos stopped interacting. They decoupled from everything around them, as scientists call it, meaning they simply stopped feeling the effects of the plasma and went their own way. From that moment forward, they traveled freely across space, carrying information about the state of the universe at 1 second old. Those neutrinos are still out there right now. Billions of them are passing through your body every second. They carry the actual imprint of what the universe looked like at 1 second old. Older than any star, older than any galaxy, older than any other signal that exists. Scientists call this the cosmic neutrino background, and the reason it matters to our story is staggering. If we could read those neutrinos, we would not be looking at the universe's childhood. We would be reading its birth certificate. The problem is detecting them. And that problem is so extreme it borders on science fiction. Right now, roughly 330 relic neutrinos are passing through every cubic inch of space around you. They have been traveling since 1 second after the Big Bang. They passed through the first stars, through the formation of galaxies, through the birth of our solar system, and now they are sailing straight through you without leaving a trace. You will never feel them. Your body is essentially invisible to them. This is the cosmic neutrino background. It is older than the Methuselah star, older than the cosmic microwave background, older than any light that has ever reached a telescope. These particles are the universe's oldest surviving messengers, and they have been carrying their cargo for 13,800,000,000 years without stopping, without slowing, without telling anyone what they know. Scientists have strong indirect evidence that this background exists. The math behind it is solid. The particle physics that predicts it has been tested in other ways and found accurate. But no one has directly detected a relic neutrino from the Big Bang yet. Every neutrino detector built so far picks up neutrinos from the sun, from supernovas, from nuclear reactors. But the ancient ones from the universe's first second are moving too slowly and carry too little energy to trigger any instrument currently built. Relic neutrinos are not like the energetic neutrinos flying out of the sun right now. Those are freshly made, packed with energy. Relic neutrinos have been cooling for almost 14 billion years. They are the coldest known particles in existence. Their temperature sits at about 1 degree and 95 hundredths of a degree above absolute zero. They are so cold and so slow that even the most sensitive detectors on Earth cannot yet feel them pass. To put the challenge in perspective, imagine trying to hear a whisper spoken before any language existed, across a distance of 93 billion light years, through walls of solid rock, using only equipment that was built to detect screams. That is roughly how hard detecting relic neutrinos is. Several experiments are currently attempting to push the boundary. One approach involves using extremely light atoms as bait. The theory says that if a relic neutrino has enough mass, it might interact with a specially prepared atomic nucleus once in a very long while, triggering a detectable event. The experiment requires incredibly precise instruments and needs to be shielded from nearly every other source of radiation on Earth. The results so far have been promising enough to keep scientists going. No confirmed detection yet, but the field is narrowing, and the stakes of success are almost impossible to overstate. Detecting a relic neutrino would give us a direct measurement of the universe at 1 second old. Every other tool we have for looking back in time hits a wall at 380,000 years after the Big Bang. The cosmic neutrino background sits on the other side of that wall. If we crack it, we crack the earliest moment in observable history. And that will either confirm what we think happened in the first second, or reveal something we never expected. What happened at 380,000 years is already strange enough to deserve its own story. There is a reason the cosmic neutrino background has stayed invisible for decades, despite scientists knowing it should be there. Detecting a particle requires that particle to do something, to bump into an atom, to release a flash of light, to leave some measurable trace in a piece of equipment. Neutrinos are extraordinarily reluctant to do any of that. Start with numbers to understand the scale. The sun fires roughly 65 billion neutrinos through every square inch of your skin every second. Those are energetic, freshly made particles, and even with that stunning number hitting you constantly, the chance of any single one of them interacting with your body in your entire lifetime is extremely small. A typical human body experiences roughly one solar neutrino interaction per year if lucky. Now take a relic neutrino. It carries far less energy than a solar neutrino, having cooled to near absolute zero over billions of years. Its chance of interacting with anything is astronomically smaller. Even passing through a detector the size of an entire city, relic neutrinos would almost never leave a mark. The current leading experiment for detecting relic neutrinos is called Ptolemy, short for Princeton Tritium Observatory for Light. Early universe, massive neutrino yield. Scientists built it to catch neutrinos using a specific trick involving tritium atoms. A relic neutrino with enough mass would occasionally interact with a tritium nucleus and cause it to decay in a measurable way. The key word is occasionally. The predicted event rate is extraordinarily rare. The experiment also faces a brutal signal-to-noise problem. Everything around the detector produces interference. Cosmic rays streaming down from space, natural radioactivity in the rock and building materials surrounding the experiment, even the vibrations from distant earthquakes. All of that noise has to be filtered out to find the single faint signature of a relic neutrino event. Ptolemy and similar experiments run deep underground, shielded by hundreds of feet of rock, surrounded by additional shielding layers, operating at temperatures close to absolute zero to reduce thermal noise. They are among the quietest places ever constructed by humans, and still the signal may be too faint to see with current technology. What makes researchers keep trying is the prize. Every other observation of the early universe relies on light, photons, electromagnetic radiation. Those tools hit a hard boundary at 380,000 years after the Big Bang, because before that point, the universe was opaque and light could not travel freely. Neutrinos have no such limit. They pass through the opaque universe without caring. They carry data from before the light ever got out. A confirmed relic neutrino detection would be the scientific equivalent of developing hearing in a species that could only ever see. An entirely new sense. An entirely new window. For now, the window stays shut. The detectors are listening. The relic particles are streaming through them every second without stopping. The scientists watching the instruments are patient. Patience is required. Because the universe keeps its oldest secrets locked behind walls that take generations to break through. The first wall light ever broke through came 380,000 years after the Big Bang. What it revealed when it escaped changed everything. For the first 380,000 years of existence, the universe produced no light that could travel anywhere. That sounds strange because the universe was intensely bright. Temperatures were extreme, energy was everywhere, but brightness and the ability to transmit light are two separate things. In those early hundreds of thousands of years, the universe was filled with a plasma so dense that photons, the particles of light, could not move more than a short distance before hitting something else and getting absorbed. Picture being inside a ping pong ball factory during a hurricane, where the balls are being fired at each other from every direction. You could not see across the room even with a flashlight, because your beam would bounce and scatter and disappear almost immediately. Light existed, but could not carry information from one place to another. That was the early universe, a fog of charged particles so thick that the cosmos was essentially opaque, hot, violent, and completely sealed from observation. During this period, the universe was also doing something spectacular and invisible. It was cooling, expanding. Every second, space stretched a little further, and the energy density dropped a little lower, and the temperature fell a fraction of a degree. The process was slow by human standards. 380,000 years is longer than our entire species has existed on Earth. But on cosmic timescales, it was quick. What happened at 380,000 years was sudden by the universe's standards. A physicist would call it a phase transition, the same word used when water freezes to ice. The temperature dropped to roughly 5,000 degrees Fahrenheit. At that temperature, electrons stopped flying around freely and snapped into orbit around protons. Atoms formed for the first time. The moment atoms formed, the fog cleared. Photons that had been trapped and bouncing for hundreds of thousands of years suddenly found a universe they could actually travel through. The plasma had thinned, the obstacles were gone, light exploded outward across space for the first time in history. What we see when we look at that light today is called the cosmic microwave background. It is the oldest light in the universe. Every photon in that ancient glow has been traveling since the universe was 380,000 years old. It has been moving for over 13 billion years, and it is still arriving at Earth right now in every direction from every point in the sky. The universe was not quiet when it released that light. Scientists studying the cosmic microwave background have found that it carries tiny temperature variations, hot spots and cool spots barely 100,000th of a degree different from each other. Those variations are a map of the density fluctuations in the early plasma, the places where matter was slightly clumped together, which eventually became the seeds of the galaxies we see today. Everything around us, every star, every planet, every structure in the observable universe, traces back to those tiny wrinkles in the ancient glow. And hidden inside that glow, a team of scientists believes they have found something else. Something that does not belong in a standard universe, something that may have traveled from further back than 380,000 years. Much further back. The release of the cosmic microwave background was one of the most dramatic events in cosmic history, and it happened in absolute silence across a sky that had no one to watch it. At the moment of that phase transition, when atoms formed and the universe turned transparent, something extraordinary occurred. Every point in space simultaneously let light go free. It was a universal unlocking. 13 billion years ago, in every direction, the universe became visible for the first time. Photons that had been trapped and scattered for hundreds of thousands of years streak outward across the newly clear cosmos. That ancient light is not faint or difficult to find. It fills the entire sky in every direction. You cannot point a radio antenna anywhere without it landing in the cosmic microwave background. It is everywhere, all at once, like a cosmic wallpaper pasted across the inside of the observable universe. Its temperature today is almost exactly absolute zero, minus 455 degrees Fahrenheit, just 2.7 degrees above the coldest temperature that can exist. Over 13 billion years of expansion, the universe stretched all those ancient photons out, draining them of most of their energy. What was once a 5,000 degree plasma glow is now a whisper of microwave radiation barely detectable above nothing. A team of researchers in the 1950s accidentally discovered it while troubleshooting a radio antenna at a laboratory in New Jersey. Two scientists named Arno Penzias and Robert Wilson kept picking up a faint hiss coming from all directions in the sky. They cleaned the antenna, checked the equipment, removed pigeons that had nested inside the horn. The hiss stayed. It turned out to be the cosmic microwave background, the oldest light in existence, and they initially thought it was interference from bird droppings. They later won the Nobel Prize for the discovery. What makes the cosmic microwave background scientifically priceless is its precision. Because it was released at a specific moment in cosmic history, and because the physics governing that release are well understood, every variation in its temperature across the sky carries real information. Scientists can read those variations like a map of the early universe. Satellites have been launched specifically to measure this ancient glow with extreme precision. The map they produced shows a universe that is almost perfectly smooth, with only the faintest ripples of difference from one spot to another. Those ripples correspond to places where matter was slightly denser 380,000 years after the Big Bang. Over billions of years, gravity pulled more matter into those denser regions. The ripples became galaxies. Galaxies became clusters. Clusters became the web of structure that fills the cosmos today. Everything visible in the night sky grew from tiny temperature differences in a glow, released when the universe was less than 1/100% of its current age. Most astronomers consider the cosmic microwave background the most important observation in the history of cosmology. But a physicist named Roger Penrose started looking at the precise map of that ancient glow and believed he saw something hiding inside the pattern, something the standard model could not explain, something that, if real, would require rewriting the very first sentence of the universe's story. Here is something you can test the next time you find an old television. Tune it to a channel with no signal. The static you see on screen, that snow of dancing black and white dots, is not fully random. A small percentage of it, roughly 1%, comes from the cosmic microwave background. Ancient photons from 13 billion years ago are physically hitting the antenna and creating visible noise on the screen. You are literally watching the oldest light in the universe displayed as TV static. This fact is confirmed. Physicists measured it. The photons in that background radiation hit Earth constantly, in all directions, at all times. Any antenna sensitive to microwave frequencies will pick them up mixed in with other signals. Most people think of the Big Bang as an explosion that happens somewhere, like a bomb going off in empty space that scattered material outward. The cosmic microwave background proves that picture wrong. The Big Bang was an event that happened everywhere at once. Every point in space was the origin. Every point in space released that ancient light simultaneously. So today, that light comes at us from all directions equally. Stand anywhere in the universe and you are surrounded by the same ancient glow. Scientists have studied this glow with obsessive precision. Satellites measured its temperature across the entire sky and mapped every variation down to 100,000th of a degree. The resulting image is the most precise snapshot ever taken of the early universe. That map revealed something unexpected. Most of it matches the predictions of the standard model perfectly, but scattered across the map are regions that are slightly warmer than they should be. Faint circular patterns, halos of heat, so subtle they are almost invisible in the noise. Most scientists who looked at those patterns called them statistical noise. Random fluctuations that only appear significant if you look for them. One scientist disagreed. Roger Penrose, a mathematician and physicist who won the Nobel Prize in Physics in 2020 for his work on black holes, started studying those warm, circular patterns in detail. He argued they were real, structured, caused by something, and the thing that caused them, he proposed, was something that existed before our universe ever began. He called them Hawking points, naming them after his late colleague Stephen Hawking. The idea behind them is radical, even by the standards of a field that regularly entertains radical ideas. If those circular warm spots are real signals, they are the oldest detected patterns in the history of astronomy. They would predate the release of the cosmic microwave background itself. They would predate the formation of atoms. They would predate everything our instruments have ever observed. They would be echoes of a universe that no longer exists. Getting to understand where Penrose believed those echoes came from requires understanding the most audacious theory in modern cosmology. A theory that treats our entire universe as a single episode in a story with no beginning and no end. Roger Penrose spent decades thinking about what happens at the end of everything. His specialty was the mathematics of extreme gravity. He helped prove that black holes were real and that they contained singularities at their centers, points where the math breaks down completely. That background gave him a very specific way of thinking about endings, about what happens when something reaches its absolute extreme. At some point, Penrose turned that thinking outward. If black holes had a final state, what was the final state of the entire universe? The standard picture says the universe will keep expanding forever. Galaxies will drift apart, stars will burn out, black holes will slowly evaporate through a process first described by Stephen Hawking, where they gradually lose energy over incredibly long timescales. Eventually, the universe will be cold, dark, and empty, No matter, no energy. Just an infinite stretch of nothing slowly cooling toward absolute zero. Physicists call this the heat death of the universe. It is considered the most likely long-term fate by most cosmologists. Penrose looked at that endpoint and saw something strange. A universe at its absolute end, emptied of all matter and structure, with only evaporating black holes still doing anything, becomes mathematically similar to the universe at its absolute beginning. Both states are described by equations that share the same deep structure. In both cases, there is no meaningful sense of time passing, because there is nothing left to measure time with. No clocks, no processes, no matter. Penrose proposed that in this mathematical sense, the end of one universe and the beginning of the next are the same thing. The death of everything becomes the birth of a new Big Bang. The universe does not die, it transforms. A new expansion begins from the ashes of the old one, and the cycle repeats. He called this conformal cyclic cosmology. Each cycle is called an aeon. Our universe is one aeon in an endless sequence of aeons, each one born from the death of the previous one, and each one eventually dying to give birth to the next. This is clearly labeled as theory, a fascinating, mathematically sophisticated theory, but one without confirmed evidence to support it. Except Penrose believed he had evidence. He believed the Hawking points in the cosmic microwave background were physical proof that the previous aeon existed. His argument was that when a supermassive black hole evaporated in the universe before ours, it released an enormous burst of energy. That burst expanded across the dying universe. When our Big Bang happened, that expanding ring of energy from the previous universe imprinted itself as a circular warm spot in our own ancient radiation. Each Hawking point, he argued, marks the grave of a dead black hole from a universe that preceded ours. Most physicists responded with serious skepticism. The debate that followed revealed exactly how hard it is to distinguish a real ancient signal from random noise. The evidence Roger Penrose presented for Hawking points was not a single observation. It was a statistical argument built on multiple studies of the cosmic microwave background map. He and his collaborators looked at the temperature map of the ancient sky and searched for regions where the temperature formed unusually consistent circular patterns. Halos where the inside of the circle was slightly warmer than the outside, and the pattern held over a specific angular size. They found a number of these halos and argued the clustering of them was too consistent to be random. The circular shape mattered. In Penrose's model, an evaporating black hole from a previous universe would release energy in an expanding sphere. When that spherical shell hit the boundary between the old universe and our new Big Bang, it would imprint as a circle on our sky, the same way a ball hitting a flat surface leaves a circular splash. To understand the scale, these rings are not small features. Each Hawking point spans roughly 8 degrees across the sky, which is about 16 times the width of the full moon as seen from Earth. They are enormous structures embedded in the microwave background, and they are subtle enough that only careful statistical analysis can pull them out of the noise. Penrose's team published multiple papers over more than a decade, refining their analysis each time. Each paper found the same result. The circular patterns were there, the statistics suggested they were real, and the most natural explanation within Penrose's framework was that they were echoes of evaporating black holes from a previous aeon. The claim drew immediate scrutiny. Science works through replication and challenge, and the challenge came quickly. 3 separate teams of researchers took the same cosmic microwave background data and ran their own analyses. Each team used slightly different statistical methods to test whether the circular patterns Penrose found were genuinely unusual or just what you would expect from a random sky. 2 of those teams concluded the patterns were consistent with random noise. They simulated thousands of random microwave background maps using computers and found that patterns similar to the Hawking points appeared in the simulations just as often as they appeared in the real data. If random processes produce the same result, the real data does not prove anything special, is there? Penrose disputed the methodology of those analyses. He argued the teams had not properly accounted for the specific statistical measure his framework predicted. The argument became technical enough that Specialists in the field disagreed among themselves about who was right. A third team later ran a new analysis using more sophisticated statistical tools and found hints that the circular patterns might be statistically significant after all. Their result was more cautious than Penrose's original claims, but it stopped short of ruling the Hawking points out. The debate sits unresolved as of today. The data exists, the patterns appear to be there. Whether they are real cosmological signals or a statistical illusion in a noisy dataset is still an open question. What makes this debate so important is not just the Hawking points themselves, it is what confirming them would mean. If they are real, our universe has a parent, and its parent had a parent, and that chain extends backward without any beginning. Science has a problem with patterns. Human brains are extraordinarily good at finding them, even in completely random data. It is one of our most powerful instincts, and in the universe's noisy ancient light, that instinct can produce false answers. The cosmic microwave background is not perfectly uniform. It contains temperature variations of roughly 100 thousandths of a degree scattered across the sky. Those variations look like the kind of random noise you would expect from quantum fluctuations in the early universe, and the Standard Model predicts their statistical properties extremely well. The Standard Model says the temperature fluctuations should have a specific pattern of variation when analyzed mathematically. Larger regions of the sky should have variations of a certain size. Smaller regions should have variations of a different size. The relationship between scale and variation follows a precise curve. Every measurement of the real cosmic microwave background fits that predicted curve almost perfectly. When you have data that already fits a sophisticated prediction this well, finding additional patterns inside it requires extraordinary evidence. Random data produces coincidental clusters all the time. Flip a coin long enough and you will get 15 heads in a row. That does not mean the coin is broken. It means random processes produce streaks and patterns just through chance. The 360 degrees of sky visible to a full sky satellite contains an enormous amount of data. Searching that data exhaustively for circular patterns of any size and any temperature contrast guarantees you will find some circles that look unusual. The question is always whether the number of unusual patterns exceeds what random chance predicts. The teams that critiqued Penrose's work argued his analysis used the wrong benchmark for what random chance should produce. When they recalculated using what they considered a more appropriate baseline, the excess of circular patterns disappeared. The Hawking points, they concluded, were consistent with a sky that had no special structure at all. Penrose's defenders pushed back by arguing the critics used the wrong statistical tools, that the specific measure Penrose used was sensitive to a signal type the standard tools were not designed to find. That absence of detection in the wrong tool does not mean absence of signal. This is a genuine scientific argument between highly capable researchers, and it is ongoing. What the skeptics have on their side is simplicity. The Standard Model already explains the cosmic microwave background data with remarkable precision, introducing the idea of a previous universe to explain a marginal statistical excess in circular patterns requires an enormous leap. It is possible. Scientists never say impossible, but extraordinary claims require extraordinary proof, and the proof so far sits in a grey zone that neither confirms nor destroys the idea. What both sides agree on is that better data would settle it. The next generation of microwave background telescopes will measure the ancient glow with far greater sensitivity. If Hawking points are real, new data should make them stand out more clearly. If they are noise, new data should make them disappear into the expected randomness. Either answer will be historic. Either the universe is a one-time event, or it is a step in a cycle that has no beginning. Both possibilities reshape what we think we are. Penrose's full theory is more structured than it might first sound. Conformal cyclic cosmology rests on a specific piece of mathematics involving something called conformal geometry. Conformal means scale-free. In conformal geometry, two shapes are considered equivalent if one can be stretched or shrunk into the other without distorting angles. Size becomes meaningless. Only the relationships between shapes matter. Penrose's key insight was that a universe in its final stage expanded to infinite size, empty of all matter, containing only light-speed particles with no mass, becomes conformally equivalent to the universe in its first instant. A universe ending in infinite emptiness looks mathematically identical to a universe beginning from a single point, if you strip away the concept of scale. In practical terms, what this means is that the death of the universe and the birth of the next universe are the same mathematical event described from two different sides of the same equation. The dying universe does not explode, it transforms. Its conformal geometry becomes the geometry of a new Big Bang, and a new aeon begins without any break in mathematical continuity. This is an elegant idea, mathematically sophisticated, internally consistent, and deeply strange. The theory makes several specific predictions. First, the transition between eons produces no net information loss. The laws of physics remain the same from one cycle to the next. Second, massive structures in the dying universe, primarily evaporating supermassive black holes, create the Hawking points in the next aeon's microwave background. Third, the new universe begins with a specific distribution of energy that inherited properties from the old one. One of the theory's predictions was tested against the Planck satellite's precise measurements of the cosmic microwave background, and the results were complicated enough to keep the debate alive. Supporters of the theory note that several statistical features of the microwave background data match what conformal cyclic cosmology predicts better than the standard single universe model predicts. Critics note that the differences are small enough to be explained by fine-tuning in how the analysis is done. The theory also raises questions it does not fully answer. Where did the first aeon come from? If the cycle is truly eternal, there is no first aeon. The chain of universes extends backward forever, and our universe sits somewhere in an infinite sequence with no starting point. Some find that deeply satisfying, others find it deeply unsatisfying because it moves the question of origin rather than answering it. For a 15-year-old thinking about this, imagine a video game where a player dies and immediately respawns, carrying no memory of the previous life, but inheriting the shape of the world that existed before. Each life is complete, each life is new, and the game has been running forever. That is conformal cyclic cosmology in rough terms. Whether it is true or not, it changed the conversation. Before Penrose developed this framework, the question of what came before the Big Bang was considered largely unanswerable and possibly meaningless. Penrose turned it into a testable scientific question, with specific predictions about signals that should exist in our sky. And across the Pacific, a different set of tools was finding things in the early universe that nobody expected. Launched on Christmas Day of 2021, the James Webb Space Telescope was built to do one thing better than any instrument ever made. It was built to see the early universe. Within months of its first light images, it delivered a shock. The telescope found galaxies, massive, fully formed, structurally complex galaxies, and they existed when the universe was only 300 to 500 million years old. A few were detected even earlier. This should be impossible by standard galaxy formation models. The accepted picture of how galaxies form goes like this. After the Big Bang, matter spread out relatively evenly. Small regions that were slightly denser than average began pulling in more material through gravity. Over hundreds of millions of years, gas clouds collapsed into the first small stars. Those stars formed in clusters merged, larger structures built up gradually, one step at a time, over billions of years. That process takes time, long periods of time. Astronomers expected the very early universe to contain only small, irregular, messy proto-galaxies, just beginning the long process of assembling themselves. Primitive, unfinished. What the James Webb Space Telescope actually found were galaxies that looked like they had already been growing for billions of years. Galaxies with hundreds of billions of stars organized into structured shapes. Galaxies with chemical signatures suggesting multiple generations of star formation had already occurred. Galaxies that by every measure looked mature at an age when the universe had barely started. One team described it informally as finding fully grown adults in a kindergarten classroom. The scientific community's response was careful. Headlines declared the James Webb Space Telescope was breaking the Big Bang Theory. Scientists pushed back on that framing. The standard model of cosmology was not broken, but its timeline for galaxy formation needed serious revision. Several explanations were proposed. One suggestion was that star formation in the early universe happened far faster than models predicted, perhaps because the gas clouds back then were denser and more efficiently cooled, allowing stars to form in rapid bursts rather than slow builds. Another suggestion was that the early universe produced far more massive stars, stars that lived shorter and more violent lives, leaving behind enriched gas that collapsed into new stars much faster than expected. A third possibility gained uncomfortable traction. Some of the early massive galaxies contained supermassive black holes at their centers, black holes so large that they should not have had time to grow to their measured sizes. They appeared to have formed almost instantly after the Big Bang, by mechanisms that standard physics cannot currently explain. Those black holes are the next layer of the mystery. At the center of almost every large galaxy in the observable universe sits a supermassive black hole. Our own Milky Way has one. It is 4 million times the mass of the Sun, and it sits 26,000 light years from Earth at the galaxy's core. Supermassive black holes are among the most extreme objects in the known universe. Their gravity is so powerful that nothing can escape from within a certain distance, and the boundary where escape becomes impossible is called the event horizon. Cross it, and the laws of physics as we understand them stop working for you. They form, according to the standard model, through a process that takes enormous amounts of time. A stellar mass black hole forms when a massive star collapses at the end of its life. Then it grows by pulling in surrounding gas and dust, and by merging with other black holes. Growing from a stellar mass black hole to a supermassive one, a factor of billions in mass, is supposed to take billions of years. The James Webb Space Telescope found supermassive black holes existing when the universe was only a few 100 million years old. One example detected in early James Webb observations contained a mass hundreds of millions of times greater than the Sun, at a time when the universe was barely 600 million years old. The standard growth model, even running at maximum theoretical efficiency with gas falling into the black hole constantly, cannot produce that much mass in that little time. This is currently labeled unknown. Scientists have multiple competing theories about how it happened. One idea is that the very first black holes were formed directly from collapsing massive gas clouds, rather than from stars, skipping several steps and starting much larger. Another idea involves specific conditions in the early universe that allowed black hole mergers to happen at an unusual rate. Neither idea has been confirmed. What the James Webb Space Telescope keeps finding, galaxy after galaxy, is evidence that the early universe was a far more efficient and violent place than models predicted. Things that should have taken billions of years to form were already present at a few 100 million years. Structures that models said required slow, patient assembly appear to have been rushed. Each discovery forces a revision. Each revision raises a new question. And those questions all circle back to the same moment. The first instant, the conditions set at the very beginning. Because everything that formed in the early universe, every galaxy, every black hole, every star, was shaped by what happened in the first seconds and minutes after the Big Bang. If those initial conditions were different from what we assume, then everything that followed would be different too. And if something from before the Big Bang influenced those initial conditions, then tracing the universe's history requires going back further than any telescope can see. That journey backward does not happen through better optics or larger mirrors. It happens through signals that do not travel as light at all. Signals that have been crossing the universe since before the first photon ever moved freely. Those signals are coming next. On March 14th of this year, a satellite called SWIFT detected a burst of gamma radiation from a point in the sky so distant that the signal had been traveling since the universe was 730 million years old. The event lasted 10 seconds. 10 seconds is how long it takes to tie your shoes. 10 seconds is the length of a short commercial. 10 seconds is nothing. But in those 10 seconds, a dying star released more energy than our sun will produce over its entire 10 billion year lifetime. The burst temporarily outshone entire surrounding galaxies, flooding space with gamma rays moving at the speed of light in every direction. Scientists logged it as GRB 250314A, gamma ray burst 250 for the year, 314 for the date. A for the first burst detected that day. The signal crossed 13 billion light years of expanding space before reaching our detectors. To picture that distance, consider this. Light travels about 5.9 trillion miles in a single year. Multiply that by 13 billion, and you get a number so large it loses meaning in human terms. The burst crossed a distance roughly 1,000 times the diameter of the entire Milky Way galaxy, moving at full light speed, and it still took longer than the age of our solar system to arrive. When it reached Earth, instruments picked it up across multiple observatories almost simultaneously. Astronomers in different countries dropped what they were doing and pointed every available telescope at that patch of sky. The afterglow from the burst lingered for hours after the initial 10-second flash, fading as the energy dissipated into space. What made GRB 250314A scientifically important was its age. 730 million years after the Big Bang puts this event at what astronomers call cosmic dawn, the era when the very first generation of stars was forming and dying. Stars born from gas that contained almost no heavy elements, because heavy elements had barely been produced yet. These first stars were enormous by modern standards, hundreds of times more massive than the Sun. They burned through their fuel in millions of years rather than billions, living briefly and dying violently. The burst from this star was one of those violent deaths. When a star of that size exhausts its fuel, its core collapses in a fraction of a second. The outer layers fall inward, hit the newly formed dense core, and bounce outward in a catastrophic explosion. But for the most massive stars, the collapse is so extreme that a black hole forms instantly at the center. Two jets of superheated plasma fire outward from the poles of that black hole at nearly the speed of light. Those jets punch through the collapsing star and blast into space, producing the gamma ray burst. GRB 250314A was one of those jets fired across 13 billion years of space directly toward us. The burst gave astronomers a rare direct view of a first-generation star's death. By analyzing the spectrum of the afterglow, scientists could measure what elements the star was made of and confirm it formed in the universe's earliest chemical era, born from primitive gas with almost no metals. Every gamma ray burst from that era is a postcard from cosmic dawn, a 10-second scream from the universe's first age, arriving at our doorstep after crossing all of time. But the story of what came before even those first stars runs deeper than any explosion can capture. The phrase gamma ray burst sounds clinical. The reality is the most violent event the universe produces on a regular basis. Start with what gamma rays are. Visible light, radio waves, microwaves, and X-rays are all the same type of thing, electromagnetic radiation, varying only in energy and frequency. Gamma rays sit at the extreme high energy end of that spectrum, carrying far more energy per photon than any other type of electromagnetic radiation. A single gamma ray photon carries millions of times more energy than a photon of visible light. When a star dies in the specific way that produces a gamma ray burst, the energy release is so concentrated and directional that it creates the brightest electromagnetic events in the observable universe. Brighter than supernovas, brighter than entire galaxies in some cases. For a few seconds, a single dying star can outshine everything around it combined. There are two categories. Short gamma ray bursts last under 2 seconds and come from the collision of two ultra-dense dead stars called neutron stars, or from a neutron star merging with a black hole. Long gamma ray bursts last more than 2 seconds and come from the collapse of massive stars, the type called a collapsar or hypernova. GRB 250314A lasted 10 seconds, placing it in the long category. The structure of a long gamma ray burst involves a sequence of events happening in rapid order, The star's iron core collapses in under a second. A black hole forms. A disk of infalling material surrounds the black hole and feeds into it at an enormous rate. Magnetic fields thread through the disk and channel energy outward along the spin axis of the black hole. Two opposing jets form and accelerate to roughly 99% of the speed of light. Those jets punch through the outer layers of the dying star. As they emerge into open space, they collide with gas surrounding the star, creating a shock wave that produces the gamma ray emission. The burst itself comes from internal shocks within the jet, as faster moving sections slam into slower moving ones. The total energy released in a typical long gamma ray burst equals what our sun would produce if it burned continuously for 10 billion years, compressed into a few seconds and fired into a beam about the width of a highway relative to cosmic distances. From Earth's perspective, we are only ever seeing the bursts that happen to be aimed at us. The jets are narrow and the universe is large. Most gamma ray bursts fire past us without detection. Astronomers estimate that many times more bursts happen than we ever observe. For GRB 250314A, the alignment was perfect. The jet from that dying star 13 billion light years away fired directly toward the point in space where our planet would eventually exist. The star died before the sun formed. The jet crossed the expanding universe, and in March of this year, it arrived. The 10-second duration felt trivial. The data inside it was extraordinary. And while that burst captured a dying star's final second, a different kind of observation was capturing the universe's very first moments. From mountaintops high enough to reach above most of Earth's atmosphere. High in the Atacama Desert of northern Chile, at an altitude of over 16,000 feet above sea level, the air is so thin that unprotected humans begin losing consciousness within minutes. Water freezes at temperatures far above what the low air pressure would suggest. The ground is so dry it has been compared to the surface of Mars. At night, temperatures plunge to -20 degrees Fahrenheit or lower. The sky above is a deep, dark violet even during the day. It is one of the best places on Earth to do astronomy. The reason is water vapor. Water molecules in the atmosphere absorb microwave radiation almost completely at sea level, which means any telescope trying to detect the cosmic microwave background from a standard location would see only the atmosphere's interference instead of ancient light. The signal from 13 billion years ago would be buried under the noise of Earth's own humid air. At 16,000 feet in the Atacama, most of that water vapor is below you. The column of air above the telescope contains a tiny fraction of the water vapor found at sea level. Ancient microwave signals can reach the detectors without being absorbed first. Several major observatories operate in this region. The Atacama Cosmology Telescope has been mapping the cosmic microwave background with extraordinary detail since 2007. The South Pole Telescope, positioned at the geographic South Pole where the atmosphere is similarly dry and cold, operates on the same principle from the opposite end of the Earth. These instruments are not traditional telescopes in any visual sense. They do not produce images you would recognize as photographs. Instead, they map temperature across the sky with extreme precision, measuring differences of millionths of a degree across millions of pixels of sky. The resulting maps look like blotchy heat images, warm spots and cool spots painted across the ancient universe. The engineering required to make these measurements work is remarkable. The detectors must operate at temperatures near absolute zero to reduce thermal noise below the signal level. Entire sections of the telescopes run colder than the space between galaxies. Vibration isolation systems keep the instruments stable against winds that sometimes exceed 100 miles per hour on the high plateau. The payoff for all that effort is access to the most ancient light ever observed. Every hour of operation adds data about the early universe that could not be collected anywhere else on Earth. Construction is currently underway on the next generation of these instruments. The Simons Observatory in Chile will combine multiple telescopes into a coordinated array, multiplying the data collection rate enormously. Further in the future, a project called the CMB Stage 4 experiment aims to measure the microwave background with enough precision to detect signals that current instruments cannot reach. Those future measurements could resolve the Hawking points debate. They could detect the signature of gravitational waves from inflation, the rapid expansion in the universe's first fraction of a second. They could potentially find the signature of a previous universe, if one exists. Or they will confirm that the universe began cleanly from a single Big Bang with no echo of anything before it. Either answer requires the absolute coldest, highest, driest places humans can build machines. And meanwhile, a different observatory was looking not at ancient light, but at something the early universe never intended to reveal. The James Webb Space Telescope cannot see visible light the way your eyes do. Its primary mirror, 6.5 meters across, and assembled from 18 hexagonal gold-coated segments, collects infrared radiation. Infrared is light at wavelengths longer than visible red, completely invisible to human eyes. You experience it as heat when you feel the warmth of sunlight on your skin, but you cannot see it. The reason the telescope was designed for infrared involves a phenomenon called redshift. As the universe expands, it stretches the wavelength of every photon traveling through it. Light that left a galaxy 12 billion years ago as visible or ultraviolet radiation has been stretched by the expanding universe for 12 billion years. By the time it reaches Earth, those photons have been pulled to infrared wavelengths. To see the earliest galaxies, you must see in infrared. Visible light telescopes are essentially blind to them. The gold coating on the mirrors is not decorative. Gold reflects infrared radiation with extremely high efficiency, around 98%. Silver, which is cheaper and more common, reflects infrared less efficiently. At the distances involved, every percentage point of mirror efficiency translates into a meaningful difference in what the telescope can detect. The telescope operates at a temperature of minus 448 degrees Fahrenheit, almost as cold as the cosmic neutrino background itself. The extreme cold is necessary because the detectors measure such faint infrared signals that the telescope's own warmth would drown them out completely. The sun shield that keeps the telescope cold is roughly the size of a tennis court. To reach temperatures that cold, the telescope sits about 1 million miles from Earth, parked at a gravitationally stable point where the combined gravity of the Earth and Sun balance each other out. At that location, the telescope can keep its cold side permanently pointed away from solar heat. The data flowing back from the telescope represents light that left its sources billions of years ago. Every image is a time machine. Looking at a galaxy 12 billion light years away means seeing that galaxy as it existed 12 billion years ago. Astronomers are studying the ancient past through the telescope's gold eyes in real time. What the telescope keeps finding in that ancient past is a universe that formed its large structures faster than anyone expected. Galaxies that look finished when they should look primitive. Stars that appear in enormous numbers during an era when conditions for star formation were just beginning. Each discovery sharpens a question that has been building through this entire journey. What set the initial conditions of the early universe so precisely that structures formed this fast? What determined the exact distribution of matter that became every galaxy, every star, every planet? The answer may trace back to a period so brief, it makes the Big Bang itself look slow. A period called inflation, when the universe expanded faster than light for a tiny fraction of a second, and the seeds of everything were planted. Return for a moment to the Methuselah star, HD 140283, the ancient sun racing through our galaxy 190 light years away. Its age is remarkable, but its chemistry is the real story. Stars are chemical records of the universe at the moment they formed. The gas that collapses to form a new star carries the exact mix of elements that existed in space at that time. Once a star forms and starts burning, it processes some of those elements, but its outer layers remain a fairly accurate chemical snapshot of its birth environment. The Methuselah star's outer layers contain almost no iron. Iron matters enormously in this context. Iron is forged inside massive stars during the later stages of nuclear burning and scattered across space when those stars explode as supernovas. Every supernova enriches the surrounding gas with a fresh dose of iron and other heavy metals. Over billions of years, as generation after generation of stars lived and died, The iron content of the galaxy's gas clouds built up steadily. A star born early in the universe's history, before many supernovas had occurred, would form from gas with almost no iron. A star born later would form from gas already enriched by countless stellar explosions. The Methuselah star has an iron abundance roughly 1/4000th of what our own sun contains. 1/4000th. That fraction is so small, it tells astronomers the star formed when the universe had barely begun producing heavy elements at all. For comparison, a star with the sun's iron abundance formed in a galaxy that had already recycled stellar material through multiple generations of supernovas. The sun formed about 4.5 billion years ago, at a time when the Milky Way had already been producing and recycling stars for 9 billion years. It inherited an iron-rich environment built up over those 9 billion years of stellar activity. The Methuselah star formed before almost any of that enrichment happened. The gas it condensed from was essentially the raw output of the Big Bang itself, almost pure hydrogen and helium, with only trace amounts of anything heavier. This makes it a direct sample of the universe's first chemical state. Studying its spectrum is as close as we can currently come to tasting the original composition of the universe's first gas clouds. The star also carries a signature of lithium, one of the few elements produced in the Big Bang itself, rather than inside stars. The amount of lithium in stars like this one has puzzled astronomers for years because it consistently measures lower than the Big Bang is predicted to have produced. This is known as the cosmological lithium problem, and it remains unsolved. Either our models of Big Bang nucleosynthesis are slightly wrong, or some process destroyed lithium in early stars, or something else happened that we have not accounted for. The Methuselah star sits at the intersection of multiple unsolved problems: its age, its iron, its lithium. Each measurement points to the same era, the universe's absolute beginning, and it raises a question that the star cannot answer on its own. What came before it? The Methuselah star moves fast. Its velocity relative to the sun is approximately 800,000 miles per hour. That is fast enough to cross the entire United States in about 20 seconds. Fast enough to circle Earth 30 times in a single minute. In astronomical terms, this speed is unusual and informative. Most stars in the Milky Way follow relatively circular orbits around the galaxy's center, drifting along in a consistent flow at speeds of a few 100,000 miles per hour. Stars that move much faster than this are typically visitors, objects whose orbits take them far from the galactic center and bring them swinging through the inner galaxy at high velocity. The Methuselah star follows a highly elongated orbit. It dives down toward the galactic plane, swings through the inner galaxy near our solar neighborhood, and then climbs back up and out toward the outer regions of the Milky Way, completing one enormous lap over an extended period. Currently, it is passing through our local region at that remarkable speed. This orbital pattern confirms what the chemistry already suggested. The Methuselah star formed during an era when the Milky Way was a very different place. Early galaxies were more chaotic, with gas falling in from multiple directions and stellar populations forming in irregular bursts, rather than the organized disk structure the Milky Way has today. Stars born in those early chaotic conditions often ended up on irregular, high-velocity orbits that persist for billions of years. The star's speed has been measured through a technique called Doppler spectroscopy. Light from a star moving toward us is compressed to slightly shorter wavelengths, shifting toward the blue end of the spectrum. Light from a star moving away is stretched to slightly longer wavelengths, shifting toward the red. By measuring how far the Methuselah star's light is shifted from what the elements should naturally produce, astronomers can calculate its velocity with high precision. 800,000 miles per hour sounds enormous in human terms. In galactic terms, it is still slow enough that the star will take millions of years to complete a single orbit. The Milky Way is roughly 100,000 light years across, and even at this speed, crossing it would take many millions of years. In the time the Methuselah star has been alive, it has completed countless orbits around the galaxy. It has passed through the galactic center region multiple times, It has survived the births and deaths of billions of younger stars around it. It has outlasted civilizations of stars that formed, burned brightly, and exploded, each one enriching the galaxy's gas with heavy elements that the Methuselah star itself never had. It carries its primitive chemistry intact across all that time and all those orbits, a relic of the universe's first age, hurtling through a galaxy that has aged enormously around it. Watching it pass through our galactic neighborhood is as close as we can come to watching the ancient universe fly by. But ancient stars are new compared to what the universe looked like before any stars existed at all. A period of complete darkness that lasted hundreds of millions of years and contained nothing we would recognize as familiar. Before there were stars, the universe was cold and dark and simple. After the cosmic microwave background, released 380,000 years after the Big Bang, the universe entered a stretch of time astronomers call the Cosmic Dark Ages. No stars, no galaxies, no light sources of any kind, just vast clouds of hydrogen and helium gas drifting through expanding space, slowly cooling, slowly clumping under gravity's patient pull. This darkness lasted somewhere between 100 and 400 million years. Hundreds of millions of years of absolute darkness across the entire observable universe. Every direction you looked from any point in space, there was nothing to see. Then the first stars switched on. The process started in the densest clumps of gas. Where hydrogen was slightly more concentrated, gravity pulled harder. More gas fell inward. The clump grew denser. The pressure at its center rose. Temperature climbed. When the core reached about 18 million degrees Fahrenheit, nuclear fusion ignited. Hydrogen atoms fused into helium, releasing enormous amounts of energy, the first light in the universe since the cosmic microwave background began to shine. Those first stars were very different from stars alive today. The gas they formed from contained no heavy elements to help it cool and compress efficiently. Modern star formation relies partly on heavy elements that radiate heat away as gas clouds collapse, allowing smaller and denser cores to form. Without those elements, the first gas clouds collapsed into far larger cores. The first stars are estimated to have been between 100 and several hundred times more massive than our sun. Stars this massive burn at extreme temperatures. They shine blue-white, pouring out ultraviolet radiation in enormous quantities. They tear apart hydrogen atoms across vast distances, reionizing the gas of the surrounding universe, which is why this era is also called the Epoch of Reionization. The first stars literally changed the chemical state of all the gas in the universe around them. They also lived extremely short lives. A star 100 times the sun's mass burns through its fuel in roughly 3 million years compared to the sun's 10 billion year lifespan. Those first stars were born, burned brilliantly, and exploded in what amounts to a cosmic eye blink. When they exploded, they seeded the surrounding gas with the first heavy elements: carbon, oxygen, silicon, iron, the raw ingredients for planets, for chemistry, eventually for life. Everything complex in the universe comes from those first enormous stars dying. The Methuselah star formed in the generation just after those first giants died. It formed from gas barely touched by the first supernovas, carrying only the faintest traces of the elements those explosions created. Every star you see in the night sky, including the sun, contains matter that passed through the interior of at least one, often several, of those early giants. You are made of elements forged inside stars that lived and died before the Earth existed, before the sun existed, in some cases, before the Milky Way assembled into its current form. And before any of those giants lit up, the universe sat in a darkness that has no equivalent in human experience. The cosmic dark ages of the universe are difficult to picture, because darkness at this scale has no reference point in human experience. Stand anywhere in the universe between roughly 380,000 years and 200 million years after the Big Bang, and the visible universe around you is completely black. There are no stars to see, no galaxies to spot, no distant glows on the horizon. The cosmic background radiation that released 380,000 years in is there, but it has already redshifted to infrared and then to microwave. invisible to any biological eye. The universe is filled with hydrogen gas, and hydrogen gas in its neutral state produces no light. It drifts, it clumps slowly under gravity, it cools further as space expands, and it does all of this in perfect, total darkness. The gas is not perfectly smooth. Tiny quantum fluctuations from the first instance of the universe left the gas with slight density variations. One region, a billionth of a percent denser than another region, a billionth of a percent thinner. These differences are so small they seem meaningless, but over millions of years gravity amplified them. The slightly denser regions pulled in more gas from surrounding areas. The slightly thinner regions lost gas to their denser neighbors. Over hundreds of millions of years, small differences became large ones. This process is called gravitational collapse, and it is the mechanism that eventually built everything. The slight density variations that existed during the Dark Ages became the seeds of the cosmic web, the vast network of filaments, sheets, and clusters that the observable universe is organized into today. During the Dark Ages, those seeds were just forming. The gas was assembling. The clumps were building. Nothing had yet collapsed densely enough to trigger nuclear fusion. The universe was holding its breath. Scientists cannot observe this period directly. There are no photons coming to us from those hundreds of millions of years because no photons were being produced. The cosmic microwave background came before the Dark Ages. The first starlight came after. The Dark Ages themselves are a gap in our observational history of the universe, a stretch of time we can only infer from what came before and after. One technique for probing the Dark Ages involves the hydrogen atom itself. Neutral hydrogen produces a very specific radio signal at a wavelength of about 8 inches. In a universe full of neutral hydrogen, this signal permeates everything. As the universe expands, that signal gets redshifted to longer wavelengths. Detecting those redshifted hydrogen signals from the Dark Ages era would give astronomers a direct window into those hundreds of millions of years. Several radio telescope arrays are being built specifically to attempt this. The Square Kilometre Array, under construction in South Africa and Australia, will eventually have enough collecting area to pick up these ancient hydrogen signals from the edge of the Dark Ages. If successful, it would give us a time-lapse movie of the universe assembling itself frame by frame from primordial darkness to the first light of stars. But the darkness itself holds a question that the first stars could not answer. Before the Dark Ages, before the cosmic microwave background, before the first second, what came before the Big Bang? This is the question that breaks standard physics and forces even the most careful scientists into territory they cannot fully map. In everyday experience, before is simple. Before breakfast comes sleep. Before Tuesday comes Monday. Time flows in one direction, and every moment has a moment that preceded it. The concept of before is so fundamental to how we experience reality that questioning it feels almost nonsensical. The Big Bang changes everything about that intuition. According to the standard model of cosmology and general relativity, time itself began at the Big Bang. Space began. Matter and energy began at the Big Bang. The universe did not explode into pre-existing space. Space came with it, and the clock that we use to define before and after started ticking at that moment. If time began at the Big Bang, then the phrase before the Big Bang is as meaningless as asking, what is south of the South Pole? There is no south of the South Pole. There is no before of the beginning of time. This is the standard answer. It is mathematically clean and internally consistent. It is also profoundly unsatisfying to most humans who hear it. The mind resists the idea of a true beginning. If something happened, something must have caused it. If the Big Bang happened, what caused the Big Bang? The standard answer is that causality itself is a property of time. And if time began at the Big Bang, the concept of cause does not apply to the Big Bang itself. There was no cause because there was no time for a cause to exist in. Several theories attempt to give the Big Bang a cause anyway, by proposing that time did not actually begin cleanly. Conformal cyclic cosmology says time is cyclical and has no beginning. Eternal inflation theories propose that our universe bubbled off from a larger, eternally inflating background, and that background has always existed, or at least has no defined beginning. Loop quantum cosmology suggests that the Big Bang was actually a big bounce, a point where a previous contracting universe reached maximum density and rebounded into a new expansion, with time continuing through the bounce. Each of these theories has mathematical structure, each makes some predictions, none has been confirmed. What they share is the instinct that something as dramatic as the Big Bang requires a context, a before, a cause, an environment in which it could occur. The physicist who first formalized the idea that time might have begun at the Big Bang was Stephen Hawking, who collaborated with James Hartle to propose what is called the no-boundary condition. In this model, time near the Big Bang is not sharp and defined but fuzzy and rounded, like the surface of a sphere. Just as a sphere has no edge, the beginning of time in this model has no sharp starting point. There is no precise moment of creation, and therefore no meaningful before. Whether that is a satisfying answer depends entirely on your tolerance for the idea that some questions have no answers, because the questions themselves contain flawed assumptions. The question of what came before the Big Bang may be one of those, or there may be an answer hiding in signals we have not yet learned to read. The search for evidence of what came before the Big Bang is not philosophical guesswork. It is an active scientific program with specific targets, specific instruments, and specific predictions that can be tested. 3 categories of signals could, in principle, carry information from before or from the very first instant of our universe. The first is the cosmic neutrino background. Already discussed in earlier chapters, these relic particles from 1 second after the Big Bang remain the oldest directly observable signal in standard physics. Experiments like Ptolemy are working to detect them. Success would give us the earliest direct measurement ever taken of the universe's state. The timeline for detection remains uncertain, but the project is active. The second category is primordial gravitational waves. Gravity waves are ripples in the fabric of space-time itself, produced when massive objects accelerate. The first direct detection of gravitational waves happened in 2015, when the LIGO detector measured the collision of 2 black holes over 1 billion light-years away. That discovery opened a completely new way of observing the universe. Inflation, the rapid expansion in the universe's first tiny fraction of a second, should have produced an enormous amount of gravitational waves. Those waves would be imprinted on the cosmic microwave background as a specific pattern of polarization, a twisting in the orientation of the ancient light called B-mode polarization. Detecting that pattern would be direct evidence of inflation. If inflation happened, it would also mean the universe expanded from an almost unimaginably small point so rapidly that regions of space that should have been in contact became separated faster than information could travel between them. This rapid expansion would have stretched quantum fluctuations to cosmic scales and turned them into the density variations that seeded all structure. Inflation predicts specific properties of those variations, and so far the predictions match what we observe, but the direct smoking gun of primordial gravitational waves has not yet been confirmed. Several experiments are hunting for the B-mode polarization signal. The BICEP array at the South Pole is 1. The Simons Observatory will search for it. The space-based mission Lightbird, planned for the early part of the next decade, will measure it from above the atmosphere. The third category is something speculative but actively studied. If conformal cyclic cosmology is correct, then the Hawking points in the cosmic microwave background are the signal from before the Big Bang. The next generation of microwave telescopes should either find them more clearly or rule them out. The Simons Observatory should provide enough sensitivity to push the debate toward a definitive answer. None of these detections has happened yet, but the tools being built today are powerful enough that the next 10 to 20 years could produce answers that have been impossible for the entire history of science. We are living in the generation that might actually hear the universe's oldest whisper, and if we do, it will raise a question that no generation before us has ever had to face as a practical matter. Suppose conformal cyclic cosmology is correct. Suppose our universe has a parent universe, and that parent had a parent, and the chain extends back indefinitely. What did the universe immediately before ours look like? Penrose's framework gives specific answers to this. The previous aeon started with its own Big Bang, its own expansion, its own formation of galaxies and stars and black holes. Over an enormous stretch of time, those galaxies evolved, stars lived and died, and eventually all ordinary matter broke down. The last surviving massive structures were supermassive black holes, the same type found at the centers of galaxies like our Milky Way. Those black holes then did something our universe's black holes have not yet had time to do. They evaporated. Stephen Hawking predicted that black holes are not perfectly black. They slowly emit radiation through a quantum mechanical process now called Hawking radiation. The more massive a black hole is, the more slowly it evaporates. A black hole the mass of our sun would take far longer than the current age of the universe to fully evaporate. A supermassive black hole, billions of times the sun's mass, would take an almost incomprehensible length of time. But in the far future of the previous aeon, that time came. Each supermassive black hole eventually radiated away all of its mass in a final burst of energy. That burst expanded outward through the dying universe in a spherical shell of radiation. The universe around those evaporating black holes was by then essentially empty, cold, and dark, so those expanding shells had nothing to stop them. In the moment of conformal transition, when the previous aeon's dying universe became our Big Bang, those expanding shells imprinted on the new universe's initial conditions. They left circular marks in the distribution of energy that would eventually become the cosmic microwave background. Those marks are what Penrose calls Hawking points. The previous universe's black holes were different from ours in one important way. They had more time. The previous aeon may have lasted orders of magnitude longer than our universe has existed so far. The physics would have been the same. The fundamental constants, the speed of light, the strength of gravity, the mass of electrons, would have been identical to ours, because conformal cyclic cosmology predicts those constants carry through the transition. But the structures would have been different. Different arrangements of galaxies, different histories of star formation, different distributions of the elements. A universe that played out similarly in kind but differently in detail. In the final stages of that universe, as the last black hole was evaporated and the last photons spread out across infinite space, the universe approached a state of maximum emptiness. Then, through the conformal mathematics Penrose developed, that state of maximum emptiness became indistinguishable from a new beginning. Our Big Bang. If this is true, every atom in your body was indirectly shaped by events in a universe that ended before ours began. The initial conditions that determined where every galaxy formed, where every star was born, where Earth appeared, trace back to the death of a world that no human ancestor ever lived in. That is either terrifying or beautiful, depending on how you look at it. A confirmed signal from before the Big Bang would be the most consequential scientific discovery in human history. The statement does not require exaggeration. Consider what the confirmation would mean at the most basic level. It would prove that our universe has a parent, that the Big Bang was a transition rather than a true origin. That time itself did not begin 13,800,000,000 years ago, but has been running in some form or another for potentially infinite duration. That single shift would rip through every branch of human thought that touches the question of origins. Physics would require revision at its foundation. The standard model of cosmology would need to be expanded to account for what preceded our Big Bang, or conditions the previous universe created, and how those conditions influenced ours. Entire new branches of physics would open up, exploring the mechanics of aeon transitions, the flow of information across cosmological cycles, and the nature of time at infinite scales. Every major religion's cosmology would face a new challenge. Most traditions that speak about creation describe it as a singular, intentional event with a specific moment of beginning. A cyclical universe without a true beginning fits some philosophical traditions much better than others. Traditions that embrace cyclical time, common in several Eastern philosophical systems, would find unexpected support in the physics. Traditions built on a single creation moment would need to grapple with what that moment means if it was itself preceded by another universe. This does not mean religion would be disproved or invalidated. Science and philosophy often describe the same reality through different lenses. But the conversation between them would change fundamentally. Philosophy would face new versions of some of its oldest questions. If time has always existed in some form, does the concept of a first cause have any meaning? If the universe cycles infinitely, does any particular moment in it matter? Or does significance become a human construction layered onto a structure that has no preferred point? For a 15-year-old thinking about where they fit in the universe, the implications are both humbling and strange. You are not just the product of 4.5 billion years of Earth history or 13,800,000,000 years of cosmic history. If the cyclic model is correct, you are the product of an infinite chain of universes, each one shaping the conditions of the next. Your existence traces back not to a beginning, but to an endless cascade of prior existence. The search for pre-Big Bang signals is, at its core, the search for whether existence has a root or whether it is a river with no source. That question is the deepest one science has ever formally attempted to answer, and the machines being built right now are the first tools in human history capable of returning useful data on it. The next 10 to 20 years will be the most important period in the history of cosmological observation. Several instruments are either under construction or in advanced planning stages, each targeting a different piece of the puzzle we have been assembling throughout this journey. The Simons Observatory in Chile's Atacama Desert will be the most powerful ground-based microwave background telescope ever operated. Its combination of large and small aperture telescopes will measure the polarization of ancient light with sensitivity far beyond any current instrument. Its primary targets include the B-mode polarization signal from inflation and the statistical properties of the cosmic microwave background that bear on the Hawking points debate. First observations are expected to begin in the mid-part of this decade, with full science data following over the years after. The CMB Stage 4 experiment, a large collaboration of American research institutions, is planned for the late part of this decade into the next. It will deploy thousands of detectors across two sites, one in the Atacama and one at the South Pole, working simultaneously to build the deepest and most complete map of the ancient microwave sky ever created. Its sensitivity will be 10 times greater than the Simons Observatory. For gravitational waves, the space-based LISA mission, which stands for Laser Interferometer Space Antenna, is planned for launch in the mid-2030s. LISA will consist of 3 spacecraft flying in a triangular formation, separated by millions of miles, connected by laser beams that measure the distance between them with extraordinary precision. Gravitational waves passing through the triangle stretch and compress the distances in characteristic ways. LISA is designed to detect gravitational waves at frequencies that ground-based detectors like LIGO cannot reach, including frequencies that may carry signals from the very early universe. The Einstein telescope, planned for construction in Europe, will be a next-generation gravitational wave detector built underground in a triangular tunnel roughly 6 miles on each side. Its sensitivity will be 10 times greater than current LIGO detectors, opening access to gravitational wave sources across a much larger volume of the universe. For neutrinos, upgrades to existing underground detectors and development of new experiments continue worldwide. The Ptolemy project is the most direct attempt to detect relic cosmological neutrinos, and its development is ongoing, with new technical approaches being tested. The James Webb Space Telescope will continue operating for many more years, pushing ever deeper into the early universe and finding more examples of galaxies and black holes that challenge current formation models. All of these instruments feed into the same fundamental question: what happened in the very first moments of the universe, and was there anything before them? The answers, when they come, will arrive not with a dramatic announcement, but with data, numbers, maps, statistical analyses. Scientists will argue over interpretations, papers will be published and contested. The process will be slow and methodical, but somewhere in those numbers, the universe's oldest secrets are waiting. Everything in this journey has pointed toward the same place. Back before the James Webb Space Telescope's gold mirrors, back before the Atacama's mountaintop observatories, back before GRB 250 314A crossed 13 billion light years. Back before the Methuselah star formed from primitive gas. Back before the cosmic microwave background released its ancient light. Back before the first atoms formed. Back before the cosmic neutrino background decoupled at 1 second. Back to the first instant. The universe we live in is vast beyond imagining. The observable portion of it alone spans 93 billion light years from one side to the other, even though it is only 13,800,000,000 years old. It contains an estimated 2 trillion galaxies. Each galaxy contains hundreds of billions of stars. Each star is a nuclear furnace producing energy at scales that make our largest weapons look like candle flames. All of that came from a point smaller than a proton. In a moment so brief it makes a nanosecond look leisurely. The physics of that first moment is where every question we have asked eventually arrives. The Methuselah star's age, the relic neutrinos, the Hawking points, the early galaxies, the supermassive black holes, the gamma ray burst from cosmic dawn, they are all echoes of the conditions set in that first instant, and that first instant itself may have been set by the end of the universe that came before it. If the cyclic picture is correct, then our universe is one note in an infinite song. Every aeon adds its verse, the previous universe's dying echo shaping the opening conditions of the next. The song has no beginning and no end. It simply plays, and we are living inside one chord of it. If the single universe picture is correct, then the Big Bang was a true beginning. The universe came from nothing, in a sense that physics struggles to define, but mathematics can approximate. And everything, every galaxy, every star, every life that has ever existed anywhere, grew from that singular moment of beginning. Both pictures are extraordinary. Both require confronting the fact that the universe existed for billions of years before the first eye ever opened to look at it. That stars lived and died in darkness for eons before any mind formed to wonder about them. That the ancient light crossing our telescopes right now has been traveling longer than life has existed on Earth. The signal NASA detected this year, the 10-second flash from GRB 250314A, crossed 13 billion years of space to reach us. The cosmic microwave background has been traveling for over 13 billion years and still fills every point in the sky. The relic neutrinos from the universe's first second are passing through everything, everywhere, right now, carrying cargo from before the first star ever lit up. The oldest whisper is not a single signal. It is everything around us, the ancient light in the background, the ghost particles sailing through our bodies, the patterns in the microwave sky that may or may not carry echoes of a world that ended before ours began. We are bathed in it, constantly. The universe has been speaking since the beginning. We are only now learning to listen. Science sometimes feels like it happens far away, in laboratories, in space, in equations on whiteboards, in rooms most people never enter. But the questions raised by this journey land directly on the question every person eventually asks. Where did all of this come from? Where am I in it? Does any of it mean anything? These questions are not new. Humans have asked them since the first person looked at the night sky and wondered what they were looking at. Every culture that ever existed developed some answer to them. Creation stories, religious traditions, philosophical frameworks, all of them built around the same human need to understand the context we exist inside. What is new is that science is now capable of testing those questions with instruments sensitive enough to measure temperature differences of 100,000ths of a degree in light from 13 billion years ago, sensitive enough to detect the collision of two black holes a billion light years away through ripples in spacetime barely larger than a proton, sensitive enough to track a dying star's 10-second scream across 13 billion light years. The data coming back from those instruments does not flatten the questions. It deepens them. Knowing that the universe is 13,800,000,000 years old does not make your life feel smaller. It makes the fact that you are here feel more improbable and therefore more remarkable. Out of all the configurations of matter and energy that have existed across billions of years, the current arrangement produced you on this planet at this moment asking these questions. Knowing that the first stars were giant engines of nuclear fire that lived brief, violent lives and scattered their guts across space, does not diminish anything. It reveals what you are made of, literally. The carbon in your body was forged in the core of a star that exploded before the Earth existed. The iron in your blood came from a stellar death. The calcium in your bones assembled inside nuclear furnaces that burned out billions of years before your ancestors appeared. You are made of stars. Specifically, you are made of dead ones. And if conformal cyclic cosmology is correct, those stars were not the first. They formed in a universe that inherited its conditions from a previous one, and you, existing here, carry the influence of a cosmic chain that may have no beginning at all. That is not a small thing to sit with. The scientists running the detectors in Chile, orbiting gold mirrors around the sun, 1 million miles from Earth, listening for relic neutrinos in underground chambers cooled to near absolute zero. They are not doing it for abstract reasons. They are doing it because humans need to know, because the question of where everything came from is the oldest question our species has ever asked. And for the first time in history, we have tools sharp enough to start getting real answers. The universe is not silent. It has been speaking since the first instant. Every signal we detect is a word in a sentence that began 13,800,000,000 years ago. We are finally learning the language. Every generation of scientists inherits a set of open questions and a set of tools. Their job is to use the tools on the questions, then hand the remaining mysteries to the next generation with slightly better instruments. Our generation inherited the Big Bang Theory, confirmed, the cosmic microwave background, mapped, gravitational waves detected, the first James Webb Space Telescope images, the confirmed age of the universe at 13,800,000,000 years. We also inherited the Methuselah star anomaly, unresolved, the early galaxy formation problem, sharpening, the supermassive black hole formation mystery, deepening, the Hawking points debate, undecided, the cosmic neutrino background, undetected. The question of what came before the Big Bang, unanswered. The next generation of detectors being built right now will close some of those gaps. The Simons Observatory will measure the microwave background's polarization well enough to either confirm or rule out many competing theories of the early universe. The CMB Stage 4 experiment will go deeper still. The LISA space array will detect gravitational waves from the universe's first fraction of a second. POLELIE, or a successor experiment, may directly capture a relic neutrino from 1 second after the Big Bang. Each of those achievements will be historic. Any one of them would rank among the greatest scientific discoveries ever made. The teenager listening to this right now exists at a remarkable moment. The answers to questions humanity has asked since the beginning of recorded history are within reach of the instruments being assembled right now. Not in some distant future, within decades, possibly within a single working lifetime. Some of the scientists who will make those discoveries are in school today, working through math problems that feel abstract, sitting in physics classes that feel distant from anything real, building habits of careful thinking that will eventually be aimed at the oldest data in the universe. The signal from GRB 250314A crossed 13 billion light years and arrived during your lifetime. The Methuselah star is still burning 190 light years away, still carrying its ancient chemistry, still waiting for measurements precise enough to resolve its exact age. Relic neutrinos from 1 second after the Big Bang are streaming through your body right now, carrying cargo from the universe's first instant. The universe has been sending messages since before the first star formed. The next generation will have the tools to read them. What they find will change every answer we currently think we have. And the generation after them will start asking the next set of questions, equipped with the answers that do not exist yet, aimed at mysteries we cannot currently even name. That is how this has always worked. That is how it will always work. The universe is older than we can fully comprehend, and we are just getting started.